Have you ever wondered, why do some industrial boilers have sand inside the combustion chamber? Sounds strange, doesn't it? What does sand have to do with boiler combustion? But in fact, this is an essential part of fluidized bed boiler technology, a highly efficient and intelligent technology, albeit with many critical considerations. Greetings to all of you who have joined today's experience sharing channel from DIVI Group. I'm Hugh. People often call me Hugh the Boiler Guy. And for many years, I've only pursued one profession, breathing life into steam boilers. Our topic today is understanding fluidized bed boilers in industry. This topic will help you understand more about the different types of fluidized bed boilers and the role of the fluidized bed material inside, also known as the bed material, typically quartz sand. This is a fairly technical video, so please pay close attention. Let's begin, shall we? Please take a moment to observe an experiment where a ball is placed over a hairdryer. The ball will levitate when the hairdryer is turned on and fall when it's turned off. This ball remains suspended in the air as long as the hairdryer operates. Now imagine that the ball is a sand grain and the hairdryer is the stream of primary air blown from beneath the grate, fluidizing the sand grains. In a boiler, if the combustion chamber contains a mass of sand, the fluidized bed material, and the primary air supply is properly arranged to fluidize the sand grains like the ball in the experiment, it is called a fluidized bed boiler. So what is this fluidized bed material for? Why is it needed? I'm sure many of you are wondering about this, right? Essentially, the fluidized bed material forms a fireball inside the combustion chamber. When fuel is introduced into this chamber and encounters this fireball, it ignites much more quickly. Therefore, it makes the fuel ignite far more easily. This is especially helpful for fuels that are difficult to ignite, such as Vietnamese coal dust, peat, anthracite, or fuels with high moisture content. This fluidized bed material forms a fireball that helps maintain a stable combustion temperature in the furnace when using fuels with low calorific value and long ignition time. The sand particles become fluidized and mix with burning fuel particles, improving the exchange between fuel and oxygen, thereby enhancing combustion. Fuel particles that remain suspended in the fluidized bed material have a longer residence time, allowing for more complete combustion and reducing emissions of CO and unburned hydrocarbons. At this point, I hope you have a better understanding of the fluidized bed material. It's precisely this bed material that gives fluidized bed boilers an advantage over other boiler types such as fixed grate or chain grate boilers. Now let's move to the next point. Is there anything special about this sand? Can it be replaced with something else? Typically, when the fluidized bed material is sand, it is quartz sand, which has high thermal resistance up to 1700 degrees and is inert, meaning it won't fracture or break. These sand grains are uniformly sized between approximately 0.1 mm and 1.5 mm, depending on the type of fluidized bed boiler. The grain size can be adjusted based on the manufacturer's design if there are special requirements. For fuels with stable ash content and particle size similar to or suitable for the air velocity or fluidizing air force, the ash itself can be used as the fluidized bed material. A specific example is rice husks, which have a stable ash content of 20% to 25%, with evenly sized and lightweight ash particles. If the primary air supply system is properly designed, rice husk ash can serve as the fluidized bed in a rice husk-fired fluidized bed boiler. The video you're watching shows the fluidization process of a fluidized bed boiler burning rice husk. Dear viewers, everything has two sides. We've seen the advantages. Now let's look into the disadvantages of this fluidized bed material. Disadvantage 1. Electricity consumption for the primary air supply fan increases dramatically. To keep both the fluidized bed material and the fuel particles suspended, a strong upward airflow must be generated. As a result, the fan's pressure head typically needs to reach 1000 H2O or more. In contrast, if no fluidized bed material is used, only 100 to 150 H2O of pressure would be sufficient. This means the fan's energy consumption can triple when using a fluidized bed compared to a regular boiler setup. Based on DIVI's field experience, using the fluidized bed material adds approximately 10,000 to 20,000 VND in electricity cost per ton of steam. However, this added cost is relatively minor, especially when burning low-grade fuels that require a fluidized bed material to achieve optimal combustion. Disadvantage 2. The fluidized bed material essentially forms a thermal fireball inside the combustion chamber, which requires a continuous supply of heat to sustain. If the boiler load remains steady and close to the design load, the combustion heat naturally sustains the fireball, which helps ignite the incoming fuel more efficiently. In this case, the heat needed to maintain the fireball is negligible compared to the combustion efficiency gain. However, at fluctuating or low loads, less fuel enters, and the fireball may not maintain its temperature, requiring more heat than the load actually demands, thus increasing fuel consumption. This is a significant drawback of fluidized bed boilers when operating under low-load conditions. Additionally, at low loads, the primary air supply is reduced and the fan pressure may be too low to keep the fluidized bed material fluidized. This creates defluidized zones where no air passes through, leading to higher emissions of carbon monoxide, CO, and unburned hydrocarbons, HC, as well as localized clinker buildup caused by uneven combustion. This represents another major drawback of fluidized bed boilers with a fluidized bed material. Disadvantage 3. During boiler startup, a significant amount of energy is required to heat the fluidized bed material that forms the fireball inside the combustion chamber, leading to longer startup times and increased fuel usage during ignition. For factories that do not run boilers continuously, 24/7, the startup costs of fluidized bed boilers with a fluidized bed material are significantly higher compared to those without a fluidized bed. Disadvantage 4. The bed material, e.g. sand, wears out over time and must be replenished regularly. This leads to a recurring maintenance kit that plant operators must plan for. The unit price of quartz sand ranges from 2,000 to 10,000 VND per kilogram, depending on type and region. Over time, this becomes a considerable operational expense for industrial users. Disadvantage 5. Quartz sand is highly abrasive. Prolonged exposure of boiler water tubes to the fluidized bed material can cause accelerated erosion and lead to premature tube failure. We've now covered 5 disadvantages of the fluidized bed material. I hope you found this helpful. If you did, please like and share to support our channel. Let's continue. Many of you may have come across fluidized bed boilers in operation where there is no visible fluidized bed, especially those using biomass or imported coal from Indonesia. Below are the 3 main reasons why some fluidized bed boilers operate without using a fluidized bed material, such as sand or inert ash. 1. If the fuel is easy to ignite and has a uniform particle size, there's no need for a fluidized bed. The fuel itself or the ash it produces can serve as the fluidizing medium. 2. If the steam demand of the plant is unstable, sometimes high, sometimes low, the boiler may not use a fluidized bed. 3. If the boiler does not operate continuously 24/7, running it without a fluidized bed can be more efficient. Even just one of these reasons can be enough to justify not using a fluidized bed. Now that we've explored the topic of the fluidized bed and fluidizing material, let's move on to the classification of industrial fluidized bed boilers. Fluidized bed boilers are classified into 2 main types. 1. Bubbling fluidized bed, BFB boilers, circulating fluidized bed, CFB, boilers. Both types use a fluidized bed material. In BFB boilers, the fuel remains within the bed until it is fully combusted and light enough to be carried away by the flue gas. In contrast, in CFB boilers, both the fuel and bed materials burn while being carried along with the gas stream. The unburned particles are then captured and recirculated back into the combustion chamber by a dedicated recirculation system. The most noticeable difference between these 2 types is that BFB boilers lack a recirculation system for sand and unburned fuel, while CFB boilers are equipped with one. For example, the video showing the combination water-fired tube fluidized bed boiler represents a CFB, as it includes a fuel recirculation system. Meanwhile, the video of the 2-drum water tube fluidized bed boiler is a BFB, since it does not include such a system. So what are the advantages and disadvantages of each design? And under what circumstances should you choose one over the other? Comparison of bubbling fluidized bed, BFB, and circulating fluidized bed, CFB, boilers. 1. Operating principle. BFB, the fluidized bed remains stationary inside the furnace. CFB, both bed material and fuel particles are carried upward by the flue gas stream and then recirculated back into the combustion chamber. 2. System construction. BFB, the construction of the BFB boiler system is simpler. CFB, the construction of the CFB boiler system is more complex. 3. Bed material particle size. BFB, bed material particles typically range from 0.8 to 1.5 millimeters. CFB, bed material particles are smaller, typically 0.1 to 0.6 millimeter. 4. Capacity range CFB, suitable for a wide capacity range from 1 to over 600 tons per hour. BFB, suitable for capacities up to 50 tons per hour. The main reasons for this limitation are as follows. Since there is no ash recirculation system in BFB, in order to achieve complete combustion, the flue gas velocity inside the furnace must be kept low to prevent fuel from being carried away. This velocity should not exceed 3 millibars. Additionally, the furnace height must be sufficient to ensure that the fuel particles remain in the combustion zone for at least 7 seconds. This results in a furnace that is very large in cross-sectional area and height. For large capacity designs, such oversized equipment leads to significant challenges in logistics and transportation. Therefore, BFB boilers are typically limited to under 50 tons watt-hour, as this allows equipment to remain within transportable dimensions. The large size of the furnace also increases the consumption of construction materials, especially metal, making high-capacity BFB boilers more expensive to fabricate compared to CFB systems. Furthermore, with low flue gas velocity comes the need for a larger furnace cross-section, which in turn requires a greater volume of bed sand. Distributing fuel evenly across a wide combustion surface becomes technically difficult. These are the key reasons why BFB boilers have more limited capacity scalability than CFB boilers. 5. Combustion efficiency relative to fuel size. For fine fuels, e.g. rice husk, ground husk, pulverized coal, finely ground bark, Craft Village sawdust, CFB is required to ensure unburned fuel particles are recirculated back into the furnace. Using BFB for such fuels will result in lower combustion efficiency because fuel may be carried out before complete burnout. Typically, BFB efficiency is 5 to 10% lower than CFB when burning fine fuels. For larger fuels, e.g. wood chips, biomass pellets, either BFB or CFB can be used effectively. The larger particle size prevents fuel from being carried away by flue gas. In such cases, both BFB and CFB offer similar efficiency, especially for capacities under 50 tons watt-hour. 6. Material consumption. BFB, lower consumption of construction materials. CFB, higher material usage due to more complex structure and additional components. 7. Fuel flexibility. BFB, less fuel flexible compared to CFB. 8. Emissions control. Both boiler types offer good emissions control, but CFB performs slightly better. 9. Maintenance costs. BFB, lower maintenance key due to simpler structure and fewer components. So those are the 9 basic differences between BFB and CFB boilers. When to choose which? If there are no specific site constraints, the CFB design is generally preferred. However, if the project is limited by floor space and the boiler capacity is under 50 tons, then the BFB design is a practical and space-saving choice. For instance, DIVI designed BFB boilers for TH Milk, 2 8-ton units, and Tuangan Oil Factory in Vinh, 1 5-ton unit, both optimized for limited space and running efficiently on chipped wood fuel. Currently, for boilers under 50 tons, DIVI offers BFB designs with unburned fuel particle recirculation. The use of a fluidized bed is optional and can be included based on project requirements. In most cases, when using biomass fuel, a fluidized bed is not required. However, if the client requests a fluidized bed, DIVI can design the system to include a fluidized bed accordingly. That wraps up DIVI's full presentation on fluidized bed boilers. We truly welcome your feedback and questions. Thank you for watching.